All right, boom. Welcome to chapter two. In this chapter two, we're going to be talking about chemical equilibrium. And chemical equilibrium happens to be a very nice area. Yeah, very simple and straightforward. You just need to understand the principles governing it, and boom, you're good to go. So let's start. Equilibrium simply means balance point, okay? When something is in equilibrium, it simply means that that thing is at balance point, right? So a chemical reaction is said to be in equilibrium when two conditions must be met. Two conditions must be met. Number one, the reaction must be reversible. And then number two, the rate of the forward reaction must be equal to the rate of the backward reaction. Rate, not amount of the forward or the amount of the backward or the quality of the forward or the quantity of the forward. No. When the rate of the forward and the rate of the backward are equal, that reaction is said to be in equilibrium, provided that it is as well reversible. So number one, reversibility sign. Then number two, rate. Very important. And the reversibility sign is usually expressed as two arrows facing one on the forward, one on the backward. At times it can be half arrows facing forward and backward. At times it can be a single arrow facing forward and backward halfway. But by the time you see a single arrow facing forward and backward, it's called resonance. So that one is actually not a reversibility sign. But unfortunately, you see that in your exam questions. It just comes like that. So let's take a typical example of a reaction in equilibrium. Let's say, for example, A plus B reacts to give us C plus D with a reversibility sign in the middle. Now, this type of reaction is said to be in equilibrium. How? Because in this reaction, A plus B combines to form C plus D, and C plus D in turn combines to form A plus B. So when A plus B combines to form C plus D, it's called the forward reaction. When C plus D combines to form back A and D, A and B, is called the backward reaction. Or you simply say that the reaction is shifting to the left. Now, there are various facts about reversibility of reactions. Various facts about reversibility of reaction, or facts about chemical reactions in equilibrium. Let's use it that word. Facts on chemical reactions in equilibrium. Number one, both forward reactions and backward reaction occurs at the same time. In other words, the forward and the backward reaction occur simultaneously. That is what we mean. Both reactions occur at the same time. So you don't need for the forward reaction to be complete before the backward reaction starts taking place. No, they take place at the same time. Number two, equilibrium can be achieved by any of the reactions. Equilibrium can be achieved by the forward reaction, it can be achieved by the backward reaction. But in most cases, the backward reaction is what meets up with the speed of the forward reaction to attain equilibrium. However, it does not mean that the forward reaction cannot meet up with the backward reaction in a given type of chemical reaction. All right, the third fact, the rate of the startup reaction is always faster than the rate of the backward reaction. Why? Because at startup, concentration is usually very high and the reaction takes place faster to produce the product than for the product to react to produce back the reactant. So at startup, the speed of the forward reaction is usually higher than that of the backward reaction. Take note, at startup. And that simply means that the backward reaction will now start leveling up until there comes a time where the speed of the backward becomes equal to the speed of the forward. And when that happens, you declare that reaction at equilibrium position, right? Now, the fourth fact and the last fact is, in a reversible reaction in equilibrium, equilibrium is attained not based by quality or quantity of substance, but however, attained based on the rate, the speed at which the forward is reacting to form the backward. So the speed at which the forward reacts to form the backward and the backward reacts to form the forward, once the speed are equal, that's a reversible reaction in equilibrium. And take note, at equilibrium, there is still movement of molecules from the reactant to the product and product to the reactant. It's not a standstill reaction. So at equilibrium, reaction is still taking place. The only difference is that the speed of both reactions are equal. So in most cases, a reaction that is kept in equilibrium can remain there for life until an external factor is brought into play. And once an external factor is introduced into the system will lose its equilibrium position for a while and then fall back to equilibrium again. And that is where Le Chatelier's principle comes into play. According to Le Chatelier, when an external factor is introduced into a system that is chemically in dynamic equilibrium, the equilibrium system will experience a shift so as to accommodate the external factor introduced, but later on will restore the equilibrium position of that reaction. And this external factor can be change in temperature, change in concentration, or change in pressure or volume, as the case may be. Take note, a catalyst has no effect in a chemical reaction in equilibrium. It only speeds up the rate of the chemical reaction. It speeds up the forward reaction that will take place, but never determines the direction of a reaction in equilibrium. Factors affecting the rate of a chemical reaction in equilibrium. The first factor there is concentration, which is the very simplest thing to do. Concentration will always affect the direction of lower concentration. Increase in concentration of the reactant will produce the forward reaction. Increase in the concentration of the product will favor the backward reaction. You get a message? It's as simple as that. So if you increase the reactant, it will form the forward. If you increase the product, it will form the backward. And there are various ways you can increase the concentration of the reactant or the product. They will just tell you increase in oxygen in a reaction between nitrogen and oxygen to form nitrogen peroxide. You can either increase one of the elements directly or increase the elements indirectly by bringing in a compound. For example, I want to increase oxygen, I bring water. That's common ion. I want to increase hydrogen, I bring hydrogen sulfide. Common ion effect. You get a message? All right, so basically that is that for changing concentration. Then that takes us to the next one there, which is the effect of temperature. Now, temperature has an effect that is determined based on the enthalpy change of the reaction. The change of the reaction can either be a positive enthalpy or a negative enthalpy. If it is a positive enthalpy, it is referred to as an endothermic reaction. If it is a negative enthalpy, it is referred to as a negative or an endothermic reaction, exothermic reaction, I want to say. A positive enthalpy is measured in kilojoules per mole, right? For example, an endothermic reaction is a reaction that does what? That absorbs heat from the surroundings. So they are more or less called heat lovers. Exothermic reactions are reactions that give out heat to the surrounding. They are also called heat haters, right? Good. So whenever you are given a chemical reaction and you're told that the change in temperature, the change in delta H is positive, it simply means that the forward reaction of that reaction is endothermic, while the backward reaction of that reaction is exothermic. If you are given a reaction and you are given a negative delta H, it simply means that the forward reaction of that reaction is exothermic, while the backward reaction of that reaction is endothermic. So for a negative delta H, which you know is an exothermic reaction, if you increase temperature, it will favor the backward reaction. Why? Because exothermic reactions are heat haters. They hate heat. They don't want heat at all. So you increasing heat in an exothermic reaction, it will favor the endothermic part, which is the reversible reaction. And if you decrease temperature in an exothermic reaction, you favor the forward reaction because they give out heat. They hate heat. That is why they give heat to the surrounding. The same thing happens in a delta plus reaction. If you increase temperature in a positive delta H, it will favor the forward reaction because endothermic reactions are heat lovers. You get it? While if you decrease temperature, it will favor the backward reaction. So basically, that is what you have to know about temperature change. And also remember, you cannot increase the temperature of the reactant or increase the temperature of the product. It is never done. Same thing with pressure. You don't increase pressure of the reactant or pressure of the product, just like you do in concentration. Everything happens in a closed vessel. So when you're applying temperature, you are increasing temperature of the entire vessel. You cannot increase the temperature of one of the components inside. It is not done. Neither can you increase the pressure of one of the components. No. Hell no. That takes us to the last part of the effects affecting a chemical reaction in equilibrium, which is pressure. Now, pressure has effect in a chemical reaction in equilibrium when two conditions are met. Number one, there must be at least one gas in the reaction because pressure only takes place in the presence of gases. Then number two, there must be an equal number of moles on both sides of the chemical reaction in equilibrium. If the number of moles happens to be equal, then pressure has no effect because volume is equal. The number of moles is approximated to volumes. After all, Avogadro told us so, that volume and number of moles are directly proportional. So the number of moles in the reactant equals the number of moles in the product. And the number of moles in the product equals the number of moles in the reactant, as the case may be, or volume I want to say. So number one, there must be at least one gas. And then number two, there must be unequal number of moles. If you have an aqueous solution or you have a liquid or a solid substance, then pressure has no effect in that area. So you're not even looking at it. You're not even counting the number of moles of those substances, right? So a typical example is you giving calcium triisocarbonate 4 decomposing into calcium oxide and carbon 4. Of course, they are gases. The only gas there is carbon 4. Marble and calcium oxide are solid. So in that case, of course, it has an effect. Pressure will have an effect because of the gas that is there. At least one gas is there. But when you have a reaction between magnesium and sulfur to give you magnesium sulfide, and all of them are solid, no reaction. And then also when you have a reaction between hydrogen and chlorine to give you hydrochloric acid, and you check the number of moles, they are equal, although all of them are gases, pressure will have no effect. Now, how does pressure take effect in a chemical reaction in equilibrium when it is possible? Increase in pressure will favor the direction of lower number of volume, while increase in volume will favor the direction of lower number of pressure, so to say. It's an inversely proportional. In fact, it depicts Boyle's law. So if you increase pressure, it will look for the direction where there are lesser number of moles, which is volume, and it will favor that reaction. If the lesser number of moles are in the product, it will favor the product reaction. If they are in the reactant, it will favor the reactant. And decrease in pressure will favor the backward reaction. In other words, when you decrease pressure, it will favor the area where you have higher number of moles. Very important. You have to remember that. It's key. So that takes us to the last part of today's work, which is laws of chemical combination. Yeah, laws of chemical combination. According to Cato Kohlberg, also called Kohlberg, and Peter Wage, the ratio of equilibrium concentration of the product raised to the power of that of the number of moles to the ratio of the equilibrium concentration of the reactant raised to the number of moles is equal to a constant called Kc. Kc stands for equilibrium constant. This law is also called the law of mass action, or simply put, the law of Kohlberg and Wage. For example, I have a reaction between A and B to give me C and D, having their number of moles as Nm and Pq. The Kc of that reaction is simply the concentrations of the product raised to the power of their number of moles to the concentration of the reactant raised to their number of moles. Take note, when the substances involved in this reaction are liquid or solids, their concentration is always declared to be a unity, which is 1. But when they are gases, then the concentration is equivalent to what is given, right? So for solid or liquid, concentration is usually regarded as 1. So Kc is the equilibrium concentration in terms of equilibrium constant in terms of concentration. Now, in a case where all of them happens to be gases, that means all the substances in the system are gases, then we talk about equilibrium concentration in terms of partial pressure, Kp. And in that note, you will now have the pressure of the reactant raised to the power of the number of moles to the pressure of the product. So the pressure of the product raised to the number of moles to the pressure of the reactant raised to the number of moles individually. Now take note. If you have Kp and Kc together, in other words, you want to find Kc when Kp is given, or you want to find Kp when Kc is given, there is a reaction that connects both of them. And the reaction is, or I say an equation, not really a reaction. And the equation is Kp is equal to Kc, all in bracket, RT raised to the power of change in number of moles of gases. And that is change in Ng. Kp is the equilibrium constant in terms of partial pressure. Kc is the equilibrium constant in terms of concentration. R is the ideal gas constant measured in atmosphere 0.0821 atmosphere liter per mole per Kelvin, or 0.8314 Pascal or kilopascal, because when you bring liter, 1 kiloliter is equivalent to 1 meter cube. So kilopascal per mole per Kelvin, as the case may be. T is the temperature, right, in Kelvin. Change in Ng represents the change in the number of moles of gases only in the product and the reactant. So you start with the total number in the product minus the total number in the reactant, only for gases. If you see solid or liquid there, you don't care about their number of moles. So their number of moles are equal to 0. Now, there is a case where Kp and Kc can be equal. And the condition that can make Kp of a reaction to be equal to the Kc of that reaction, it is when the change in the number of moles of the gases in the reactant and the product are equal. And that simply means that by the time you find the difference, you have 0 as your delta G, delta Ng. And when you have T, R, all raised to power 0, that will give you 1. And therefore, Kp and Kc become equal. Good. Now, before we go into some facts on chemical equilibrium constant, it's important for you to know that they can give you a particular chemical reaction in equilibrium that can even lead to quadratic equation. Oh yes, we see questions like that, and courtesy demands that you know what to do when those type of question appears. First, they will give you an equation and tell you that this equation is in equilibrium. They'll give you the concentration of the reactants, or they will give you the number of moles and the vessel volume so that you can calculate the concentration. And once you are able to calculate their concentration, or they give you the concentration of each of the substances, both at the reactant and the product, they will tell you that it is in equilibrium. And you are asked to calculate the concentration of a particular element either in the reactant or in the product when a particular amount of a substance is added. So the first thing you will have to do is to first of all calculate the equilibrium constant of the reaction. Get the Kc of the reaction. Apply the concentration of the product all over that of the reactant, get your Kc. The Kc of that reaction is equal to the Kc even when a new substance is added, because it will surely restore back that same Kc. That is Le Chatelier's principle applied. So once you get your Kc, the next thing you're going to do is to now derive the new concentrations of the reaction on addition of X amount, depending on the amount they're asking you to add. Maybe they're asking you 0.1 molar is added, or 0.1 mole of A and B is added. So what will be the concentration of A at equilibrium? Simple. Since 0.1 mole, convert it to molar because you have to divide by the number of the volume of the entire vessel. Since that number of mole in molar has been added, which is the reactant, of course it's going to favor the forward reaction. It simply means that the concentration of A at first will be the initial concentration plus X. While the concentration, not plus X. At equilibrium, the concentration of A and B will decrease, while the concentration of C and D will increase. That's the truth. At startup is increased, but at equilibrium it will decrease. So the concentration of A and B will decrease by X, while the concentration of C and D will increase by X. But before there will be increase or decrease in concentration, initial concentration will now be, if the initial concentration of A was 0.2, now you are adding 0.1 molar. It becomes 0.3 molar minus X, which will now take place at equilibrium. So if maybe B was 0.3 molar, and now you are adding 0.1 molar, and sorry for that call, minus X, which will happen at equilibrium. So by the time you do that, AB will have a decrease, that is minus minus, while CD will have an increase, which is plus plus X. Multiply the 2 at the top, multiply the 2 at the bottom, and that's going to give you a quadratic equation. You can solve that quadratic equation using the almighty formula, and once you're done solving it with the almighty formula, you get the value of X. So for you to now get it from it, For you to get the concentration of B, you have to subtract X from it. For you to get the concentration of C and D, you have to add X to it, that value of X that you got. And boom, that settles that problem. So you can have potential questions that will come and you have quadratic equations in cases. Just take note of that. Then that takes us to the last part, which is the factors or facts about equilibrium constants. So we start with the first fact there. When a given reaction in equilibrium is the reverse of another reaction in equilibrium, then their cases is simply the reverse of each other. What do we mean? You have the first equation, A plus B giving you C plus D. Then the second equation is actually the reverse of the first one. That is to say, you have C plus D giving you A plus B. And you are asked to calculate the Kc of the second reaction. It's simply the reverse. So if the Kc of the first reaction is N, for example, then the Kc of the second, which is the reverse of the first, is simply 1 all over N. You can prove it. Just substitute your variables and you are good to go. Good. So next, when the difference between one chemical reaction in equilibrium is just a multiple factor, then the Kc of the second reaction is just the Kc of the first raised to the power of the factor in question. I will explain. You have two reactions. The first is A plus half B to give you C is 2A plus B to give you 2C. You get it? Good. Now, if you check the two reactions, you just discover that the second reaction is just 2 times the first reaction. So what we're saying is that if the Kc of the first reaction is N, the Kc of the second reaction will be what? N squared. N squared. So it's going to be the power of that factor of multiplication. Then that takes us to the last one there. When the sum of the two chemical reactions in equilibrium equals the third chemical reaction in equilibrium, then the Kc of the third reaction is simply the product of the two Kc's of the initial reactions in equilibrium. What are we trying to say? If the sum of two chemical reactions in equilibrium is equal to the third, the Kc of the third is simply the product of the two chemical reactions initially in equilibrium. For example, A plus B will give you C, that's Kc1. Then C plus D will give you E, that's Kc2. Then, by the time you add A plus B, that's the reactant of the first plus the reactant of the second, and it gives you A plus B plus D, then, which is equal to E. Then what we are saying is that Kc3 is equal to the product of Kc1 dot Kc2. Because on adding the reactants, you will have A plus C plus B plus D. On adding the product of the first two, you will have C plus E. Then C can cancel out each other, and then you'll be left with A plus B plus C plus D giving you E. So the product of such Kc of the first and second equals the third. That is what we're saying. All right, thank you for your time. God bless you, and we're good to go. Boom.